Okay. Tim, do you want to do a quick intro?
Yes, okay. So Tim Wolf, actually I'm a WEF delegate for the Chesapeake Association and actually, consulting engineer, environmental engineer with KCI, like chief engineer, been here 22 years, wastewater. So excited to hear about your presentation. So thank you.
All right, Tracy, do you want to chime in?
Yes, hi there. I'm Tracy Storm, Executive Administrator for CWEA, and this is my first experience with the student design competition, so I just wanted to observe and take a look at what's going on. So.
Great. All right, Jessica.
Hi, my name is Jessica Shao. I am the chair of the Student Career Fair for CWEA, and I'm also a project manager at WSSC.
Great. Okay. And also, just to list the folks who unfortunately aren't on the call today, Kui Lin is a design engineer with KCI, works with Tim. Jessica Oakes with EA Engineering, and then also Justin Hall and
hi, Chris. I'm actually here.
Oh, great. Okay. Didn't realize that.
This is Justin Hall. I'm the project manager at JMT.
Excellent. And then also Ellen Friketic, I don't think she's joined, but she's a manager at MES in the water wastewater group. So, and also Monty Simon with JMT is also on the committee and couldn't join this morning. So, all right, I'll turn it over to Azam and your team to introduce themselves before kicking off the presentation.
Thank you, Chris. I'd like to thank the CWEA leaders and all the review members. We are deeply grateful to all of you to make time and be flexible with our team. So we have, as I said, our head of the department, Dr. Behera here, and I will like the student to introduce themselves. Stephanie, maybe you can take the lead from here. Okay, good luck.
Okay. Hi, my name is Stephanie Fuentes. I am a master, getting my master's. I'm doing my master's at the moment at the University of District of Columbia and water resources. And my specialty, I'm hoping, is going to corrosion engineering.
G.
Oh, you're on mute, G.
You're on mute, G. Yeah, go ahead.
Sorry. Hi, my name is G. Shin. I am also a master's student at the University of District of Columbia. I am doing my master's thesis in geotechnical engineering.
Hadi?
Hi, this is Hadi I'm basically senior, graduating right now, and I guess that's it.
Okay. Armani? Armani, can you hear us? Hello? Maybe she can, so Armani, your microphone, maybe we'll come back to Armani. Kevin, go ahead.
Good morning, everyone. My name is Kevin Turcios. I completed my junior year at UDC, and I'm an upcoming senior in this fall.
Assefa?
Hello, everyone. My name is Assefa. I'm a civil engineering major. I'm a junior as well.
Lirane?
Hi, my name is Lirane Mandijoupa, and I am an undergraduate student, actually a senior in civil engineering and mathematics.
Sure, I think Armani, let's try with you one more time if your microphone is working.
She's saying that her mic is on mute and it won't unmute her, so she might go out and again.
Hi, Armani, we can hear you now.
I'm sorry, I had to read. Okay,
can you introduce yourself?
My name is Armani, and I'm an undergrad, and I recently graduated this May.
Okay, thank you. Dr. Behera, you want to quickly say something? Your microphone is off.
Yes, I'm really thankful to Dr. Azam, who is leading our team in environmental engineering, and he joined us in the fall of 2019. He came from Manhattan College, where he was there for 5 years, and he was in DC area prior to that. And I'm very happy that he's leading this team and taking care of our expertise in the environmental engineering.
Thank you, Dr. Behera. So, and myself,
good luck for the team.
Thank you, Dr. Behera. So myself is Hossain Azam. I'm a assistant professor in environmental engineering at UDC. I'm actually a byproduct of a design competition. I did this design competition in 2008, so that the review team knows. And I'm deeply passionate about this, and I'm very actively with WEF. And it was led by all the students. And I said that before, but I want to say I'm very proud today that they are presenting. Stephanie?
Okay. So I'm going to take charge now. So let's see.
Chris, we are ready to go.
Okay.
Are we ready to go, or?
Yes. Yeah, that's fine. Are you able to control the screen, or do I have to give you permission? Okay. No, you got it. Okay. Good.
Good luck.
Okay. Good morning, and thank you everybody for joining us today in the virtual presentation for our project and for the competition. So our project today is about the performance evaluation of existing wastewater treatment plant and subsequent future expansion to meet stringent nutrient goals. Now, the team members that are joining us and they will be presenting today are Kevin, Armani, Lirane, Assefa, G, me, and Stephanie. And so that we have two steps for our design, for our whole design. And the first one is for the present, which is the performance evaluation of existing wastewater treatment plant, and which we have to try to meet our goals for the concentration of specific things in the water, like the nitrogen, the phosphorus, and also we have step 2, which is the subsequent future expansion to meet stringent nutrient goals, and which is going to be for the future. So this is our ultimate goal for our system, that it has to meet. It has to meet this criteria for the nitrogen and for the phosphorus. And now so our system follows the NPDES permit limits, and we have to comply with that. So our system does not have the things that are not permitted by the NPDE, like the E. coli, the nitrogen, like the ammonia, the phosphorus. Now that's for the present criteria and also for the future. Now for the future, our system always tries to aim at doing better, trying to have always less concentration of specific nutrients and specific things that are not good for our health. Now, that's our system that will be trying to focus more in the future, but it's also designed mainly on the present to fix whatever problems are there. And I'll give the lead to Stephanie.
So this is the existing facility. The wastewater treatment is located in the western part of the United States, and it has two distinct treatments. It has the liquid stream train and the solid stream train. And this is the parameters we use when we were using our design. The existing treatment plant had an average daily flow of 90,840 cubic meters per day, and had an average day maximum month flow of 100,009.8 meter cube per day, and it had a peak instantaneous flow of 200,932 meter cubes per day. This is the system. This is the liquid treatment unit for the wastewater treatment. As you see, it has a influent screen, the grit bias, grit handling, the primary clarifiers, the aeration basin, a side stream treatment, blowers, a second clarifier. It has a trisery filter, disinfection. It has for the weights, weight lens, and natural chain system, and an influent pump station. The solid station, it actually treats Class B biosolids, and the same thing, it has its own units. It has a primary slug screening, a slug grinding, a primary slug thickening, a primary slug fermentation, a polymer system, a digesters for the sludge mixing, heating, dewatering convenience, a digester for the gas convenience, and a cogeneration. In our design, our three main goals was to make sure the biological nitrogen and phosphorus were removed. We had a triceri treatment, so any other stuff that was inside the wastewater will be able to be treated, and a sludge treatment, because after all this, we had sludge in the end. Now it's to Kevin.
The evaluation of the system condition was done using BioWind Simulator, which is used to analyze and design wastewater treatment plant. And this is a diagram of the existing condition in which we created. In the next slide, I will go more in depth.
Kevin, we cannot hear you.
Lirane or?
Kevin?
So while designing our wastewater treatment plan, we had to meet the following objectives, which are that we had to maintain our concentration of total nitrogen between 4.8 to 8 milligrams per liter. Our biological oxygen demand had to be less than 10 milligrams per liter. Our total suspended solid had to be less than 10 milligrams per liter, and our total phosphorus had to be less than 0.1 milligram per liter. Our ammonia had to be between 1.6 and 3.8 milligrams per liter. Our nitrate and nitrate had to be between 1.6 and 3.8 milligrams per liter. So as Stephanie mentioned before, we had a flow of 90,084 cubic meter per day. Our chemical oxygen demand was the combination of the biological oxygen demand and total suspended solid. And to get our total case-dal nitrogen, we had to combine our TKN and our ammonia nitrate. And as you can see in the next slide, Stephanie, can you move to the next slide?
Kevin, your mic is off.
Sorry.
Kevin.
This is the treatment units of treatment plant model for our model. This consists of a grid tank, a primary clarifier, a 5-stage Barton flow with anaerobic, anoxic, and aerobic tanks. We also had a secondary clarifier, a digester tank, a side stream treatment, which is our nitrification and denitrification process. These are all required based on the project description. And we input our volumes and dimensions given based on the project description. We found the total volume of all the units to be 96,715 cubic meters. Next. So this is the first stage of our BioWind model and what is required by the project description. The first thing is the introduction of raw influent coming into the treatment plant from homes and businesses. Then water enters our grid tank, which removes inorganic solids and from the raw wastewater before entering the primary clarifier. It then enters our primary clarifier. However, we use a settler in our BioWind modeling because it was more effective in removing organic solids. And in this stage, it creates a hydraulic line and also a sludge line. Thanks. And the second stage of our BioWind model is the 5-stage Barton flow, which removes nitrogen and phosphorus from the water. It first passes the anaerobic tank, where polyphosphate accumulating organism release phosphorus and capture volatile fatty acids. Water then enters the anoxic 1 and 2, aerobic 1 and 2, anoxic 3, and aerobic 3. And then an aerobic tank, phosphorus is absorbed and volatile fatty acids is released. It also removes chemical oxygen demand to CO2 and converts ammonium to nitrate. In the anoxic phase, nitrate is converted to nitrogen gas. And we had to insert internal recycling, and the ratio was 11 cubed, which was helped with pumps. We also had to introduce fermentate to provide an extra source of carbon, and we did not decide to use methanol because there was already some carbon in the system. Next. So this is a third stage of our biowind model. Before entering our primary clarifier, we introduced 190.4 kilograms a day of aluminum sulfate to remove excess phosphorus. It then enters our secondary clarifier, where we remove biomass from the tank from the final influent, and then send some of the sludge to the digester for further processing. Before leaving the influent, we added a dewater unit which removes excess sludge and separates the water. It then enters our influent. However, before exiting, typically we have to introduce a disinfectant such as chlorine, and then we have to dechlorinate with sodium sulfite and bisulfite. Next. So this is more detail of our sludge process for our model. So the first thing is all the sludge, it enters through our pumps where it's sent to our holding tank. And we input our holding tank in our system to not overwhelm the digester. And then the sludge enters the digester where it breaks down organic waste from the clarifier. It then enters the dewater unit, which separates excess liquid or centrate to be sent to the nitrification and denitrification process. Sludge is removed from the treatment plants as biosolids. Next. So this is our stride treatment process of our model, which is basically our nitrification and denitrification stages, where we remove nitrogen from the centrate of the sludge, and we recycle some of it back to the first stage, which is our garden pool stage. In this stage, we also had to introduce methanol, and we introduced 7,820 kilograms a day of methanol to provide additional carbon for denitrification. We also added a 3 molar line to control alkalinity in the water. Next. So based on our model, we were able to meet the present treatment goals. So for total suspended solids, to reiterate again, our goal was to fall between 4.8 to 8 milligrams per liter. As you can see in the purple, it's 4.3, which falls below that range. For our biological oxygen demand, it had to be less than 10 milligrams per liter. As you can see, and the red is 0.8 milligrams a liter, so it successfully passes. Our total suspended solid, again, had to be less than 10 milligrams per liter. As you can see, and the blue is 0.2, which falls below that range. And for our total phosphorus, had to be 0.1 milligrams per liter, which in the orange, it meets the criteria. And then ammonia had to fall less than 3.8 milligrams per liter. As you can see in the blue, it is 0.5 milligrams per liter. And then finally, nitrate had to be less than 3.8 milligrams per liter. And in our system, it was found to be 2.2 milligrams per liter. Next. We also calculated the solid retention time in the hydraulic retention time of our system. So the total hydraulic retention time of our system was found to be 4.98 days or 5 days. We also calculated the solid retention time of the aerobic tanks, and it was found to be 2.82 days. And then we calculated the whole total hydraulic retention time for the whole system, which is found to be 10.56 days. Next. To design our model to meet the future criteria, we tried to improve our model using chemicals only. Next slide. So two of the main chemicals we were trying to change and test out to improve the quality of and efficiency of our system was to basically work around with methanol and alum. So as you can see, for methanol, we were able to decrease to 11,880 kilograms per day. And alum, we had an increase to 230.8 kilograms a day. And for the alum number 2, which is right before the exiting our influent, it remained the same. So in our future scenario, the goals were partially met. Biological oxygen demand was met, total suspended solids were met, total phosphorus were met, ammonium was met, nitrate and nitrite was met. However, we were not able to meet the total nitrogen goal. So we had to look into alternative solutions to change the system. Next.
Your microphone is off, Lirane.
Sorry. So for our present scenario, the cost distribution is, as you can see, with most of our costs fall into the power categories and fuel, and the cost per hour for power is $621.62 and 5,445,389. And for the fuel, the cost is $138.52 per hour and $1,213,435. Next slide. And also for our cost analysis, we see that most of our power demand falls into the pumping, which means that we spend most of the power is spent on pumping, and that is 7,933 kilowatts, which gives us $459 per hour and 4,021,978 per year.
Okay.
Sorry. Our alternative techniques to meet our future criteria, like Kevin said, since we couldn't meet our nitrogen and phosphorus, we look into alternative techniques. The 6 ones that we did investigate was IFAS, was an integrated fixed activated sludge, the Lirane, which is a single reactor system for high activity for ammonium removal over nitrate, ANAMOX, which is an aerobic ammonium oxidation, ANITAMOX, which is like the ANAMOX process, the NPR, which is a membrane bioreactor, Australia Pearl reactor, and a faux strip process. I'll hand it over to Armani.
The IFAS is a free-floating medium to an activated sludge basin that helps enhance the treatment process by stimulating the growth of biomass on the media. Also, aeration is used during the activated sludge process. It is when the air is added to water to help promote the microbial growth. Next slide. Some advantages and disadvantages of IFAS would be that it increases the process stability and it improves sludge retention time. A disadvantage would be that it costs a lot to construct and operate this system. Next slide. The Shin is a method that is used to help remove nitrogen from wastewater through nitration and denitration. Nitration is the process of ammonia to nitrate, and denitration is the process of nitrate to nitrogen gas. Next slide. Some advantages of Shin will be that the activated shell systems for nutrient removal are flexible, robust, and cost-effective for treatment of wastewater and house and industrial wastewater. A disadvantage would be that the biological nutrient removal is very tedious and requires the main parameters to be constantly supervised. Next slide.
As Armani just discussed, those are two methods of ammonium removal from wastewater. Anammox is another method for ammonium removal. Anammox stands for anaerobic ammonium oxidation, and this is a process which was discovered in 1999 that occurs due to a special type of bacteria. This is a two-step process, and in the first step, half of the ammonium present in the wastewater undergoes nitrification and becomes nitrite, hydrogen, and water. In the second step, the remaining ammonium in the wastewater, along with the nitrite that was just created, is processed by these special bacteria to make nitrogen gas and water. Next. Some of the advantages of anammox is that although it occurs in two separate steps, both steps can occur in the same vessel or tank, reducing cost of installation, along with less energy consumption, because in the first step, aeration is required, but because you only have to convert half the ammonium to nitrite, it requires less energy. Some of the disadvantages are that these bacteria are slow to grow. They take 10 to 14 days to double. And that's a problem because if there is accidental sludge loss, then it takes a relatively longer time for the system to recover. Next. Anammox is a trademark on anammox, essentially. It's an application of anammox. It employs anammox along with MBBR, moving bed biome film reactor. Essentially, anammox is grown on floating media, which makes the system more efficient. It incorporates the same nitritation and anoxic ammonia oxidation as anammox does. Next. Some of the advantages of anammox are that it is more economical, it takes up less space due to employing MBBR. It produces 90% less sludge production, which means less taking away sludge from the facility and having to treat it. It uses 60% less energy consumption, due to less aeration being needed, and also requires no carbon source in the denitrification site process. The disadvantage is that it is more expensive to set it up in the beginning. Next. The membrane bioreactor, or MBR, combines the membrane technologies, such as microfiltration, ultrafiltration, with the biological treatment process. It's become more widely available due to recent cost reductions in membrane production costs. Next. Some of the advantages are that the hydraulic retention time and the solid retention times are independent. The effluent is of high quality. It's fairly simple, so it's consistent in performance, although there is some maintenance. It produces low sludge amounts and requires less sludge dewatering. The disadvantages are similar to any of these additional methods. It's a higher capital and operational cost. And the operation of the membranes especially is kind of complex and requires specialized personnel. Next. So we've been talking about ways to remove ammonium from the wastewater. Another contaminant of concern is phosphorus. This is the chemical that causes dead zones in our waters, where nothing but plants essentially grow. The Pearl reactor addresses this phosphorus level by, it's a self-contained tank that you can attach to any wastewater system, and it controls phosphorus by removing it through the precipitation of struvite, which is magnesium ammonium phosphate. Some of the advantages are you remove phosphorus from wastewater, which helps reduce eutrophication of receiving water. And you can sell these struvite crystals as it's a fertilizer. It's a very pure phosphorus fertilizer, so they're already registered and available as a commercial fertilizer. So although the disadvantage is the higher initial investment, it can be recouped through fertilizer sales. Next.
The photostrip process is a method where the microorganisms in the activated sludge are bioaccumulated and secrete phosphate. This is a side stream process where only a part of the recirculated sludge is passed through the aerobatic tank, and the mainstream is where all the sewage is passed through the aerobatic tank. The main purpose of the photostrip process combines both biological and chemical process for the removal of phosphorus, which is what we really needed in our system. The advantages of the photostrip process: it has no additional heavy metals contaminated of the sludge, no negative effects on the acid capacity, no additional sterilization of receiving water course, nor less chemical cost, nor less chemical storage or handling, and unaffected by the effluents and treatment plant influent. Some disadvantage though, some bacteria can be grown on the filament that comes from the scum formation. From these techniques and all these advantages, we are going to be able to utilize it to meet our present and future criteria. Since our future criteria, we could not remove all the nitrogen and phosphorus, we plan to use it in the future so we can actually make our system better, more cost efficient, and to meet all our criteria goals. This is our system. It was a 201 system, and it was accomplished by the BioWin 6.0. We were able to meet all the present criteria and some of our future criteria, minus the nitrogen and phosphorus limits. For this reason, if we are selected by the next round, we will be able to use the alternative technique that we learned to compensate for the nitrogen and phosphorus limits. This can help reduce and increase the efficiency for our design system. We would like to thank all the CWEA leaders who are here with us. Christopher Overcash to actually be here and take your time and listen to our presentation. All of the UDC faculty members and staff members, the students, our civil director, our civil engineering director, Dr. Behera, and a big special acknowledgement to our advisor, Dr. Hossain, Dr. Azam, because he's like him, he spent days helping us with this. And thank you very much for listening. And if you have any questions, it's open floor now. Thank you.
Thank you. Chris, it's to you.
Yeah, great job, everybody. Yeah, I think you did very good at presenting a very technical subject. So yeah, I'll start off with a a couple questions that I thought of as you were discussing the scenarios. So first of all, I wanted to know how you came up with that location. And I'm assuming it's an actual site.
I can answer that because I worked as a client for them, so I had a actual treatment plan description that I gave it to them. Like, this is the existing treatment plans, and this is the treatment goals we have. Go, and this is the typical dimension, and then go design it so that it can meet the goals. So that was I was the client for them, and I gave them those criteria to meet the goals.
Gotcha. Very good. Very good. And yeah, I could tell, it was a real world situation or scenario. So it's good to hear that. Next question that I had, how did the team come up with the cost estimates that you were displaying? What was what were your sources for those?
So most of our cost estimates was done by BioWin 6.0. It's already included in the labor. I think Kevin Lirane can explain it a little bit more.
Yes, so BioWin gave us the power demand and the cost per hour. The only thing we had to calculate was the cost per year, but all these numbers were given by BioWin, the software, except for the cost per year. So it was given.
Okay. So in many, just to throw this out, in many scenarios where we're working up cost estimates for clients, they'll ask for multiple sources. So it sounds like you used a single source. Not that it's bad. I'm just throwing it out there for for your future use in your careers, that they'll look for multiple sources.
Okay, thank you.
Can I add one thing, Chris? I know the students are going to answer. Look, so they are planning on doing that, but they had only 2 weeks, so they could not reach to all the companies,
Sure.
and all the companies are now closed, right? They hardly answer this type of friendly calls to know all the details. So I think that COVID-19 has affected some of the preparation. Thank you.
Yeah, that's a great point. We're actually seeing some of that too. The teams just not having folks in the office to respond quickly. So very good point. Yeah, those are the 2 main questions I had. I'll turn it over to any of our other folks on the call to ask any questions that came up in your minds.
Okay, this is Tim Wolf. I'll go ahead and ask a few questions, but overall, yes, a nice presentation. Very good technical presentation of looking at the different processes, talking about BioWin. I thought it was good at the beginning that you had treatment objectives. You clearly laid out what your goals were in your immediate and future. So someone looking at this presentation knew exactly what you're shooting towards right up at the beginning. There was a few things that I had some questions on. Was you talked about through your process, you mentioned a dewatering unit after the secondaries, but you didn't explain what type of unit it was, didn't have an idea of what you were talking about. So, either you can answer it now or clarify that a little further, but that's what I remember as I was jotting down comments. And then, that was like the solids dewatering unit. Then the 3M line, it wasn't clear on what that was when you were talking about it. You kind of glazed over it. You may want to explain it in a little more detail. And then you talked about the SRT, and you gave the SRT for the tankage, and you gave the results, but you didn't compared to standards in the industry? Are they considered within standard ranges or not? You just listed the SRT, HRT of the facilities, and how's that compared to standard practices? So that may be something you want to note on. I don't know if anybody wants to comment on that, but and then let's see, goals partially met. Let's see, I'm just reading my notes, so I'm sorry that it's kind of cut up here a little bit. Well, I guess the other thing I know, going into the future options, you went through, quite a few different processes, and which was good. You looked at alternatives, but I think in summary, you should have maybe a summary table listing all the options for nitrogen and phosphorus, and you kind of gave the advantages and disadvantages. You can do like a pairwise comparison, the pros and cons, and which is kind of leading between the treatment options. I don't know, maybe you didn't have time to do that, but to me that, I wasn't sure in the end for the future considerations, what were the advantages? Because there were some things were maintenance heavy and operations heavy, and then some of them were more efficient with, energy cost and construction cost. So it would probably be good to have a summary table on that. So those were some of the things that I noted. Let's see if there's anything else. Sorry. No, because like you mentioned about this, the advantage of the struvite fertilizer, obviously that's a cost savings because you can generate some revenue to offset your operation costs. So that's why I thought a summary way be good. So I don't know if anybody wants to weigh in or have any clarifications on my questions.
I can answer some of the alternative processes. No, that's a really good thing. I think when we were trying to present it, we didn't want to go too in depth with it because we really wanted to present more on our model for BioWin. So we did the alternative processes. I think we were thinking of like just a quick summary of exactly what it was and the advantages and disadvantages. And for the cost estimate, no, you're right. So I think next time we are going to put like a nice little summary table.
Yeah.
And for our next one, we'll definitely do that. We'll actually mention a little bit more about how this can actually help the nitrogen and phosphorus, since this is what we actually could not achieve for our future goals. Okay. I know the SRT and the HRT, they use the BioWin, and I know Lirane did use a formula. Lirane, did you know which one you used?
Actually, the SRT's number and the HRT's number were given by BioWin as well. I just wrote down the formula so you guys can know, where those numbers come from, but we didn't do any calculation for the SRT. BioWin generated those numbers.
Right. The question was, how's that compared to the standards for, that particular process? Are you with those SRT, HRTs, do they meet within the ranges for that type of process? That was treatment part. That was my question.
Kevin actually said that he actually did calculate it.
Okay.
I can also talk a little bit about the questions about the dewatering units.
Okay.
So we had to put a dewatering unit after the digester tank. The reason was because we were modeling the system. We were getting errors when it started to enter the denitrification and nitrification zone. So we had to remove all the sludge from going into that system.
Okay.
And we also in the influent, as the dewatering unit before the influent, when we were modeling the system, there was some suspended solids. So we had to insert a dewatering unit to separate all the suspended solid from the system.
Yeah, now but the question is what type of unit? I mean, you know, what process are you looking at to do that? I mean, that was the question.
Hey guys, this is Justin. So I was just thinking, would it make sense, Chris, for us to kind of come up with our list of questions like we did for the other team and send that out to this team, just so it's kind of an apples to apples situation, and they get the time they can formulate responses to some of these questions?
Well, yeah, so there's going to be that step as well, because we have folks that are going to listen to the recorded version. But yeah, I figured we would just have an open discussion as well.
Okay.
So yeah.
So maybe some of these questions we can also put in that list for them, and they can have some additional time to look at them.
Yes, yeah, and I should say to UDC team, yeah, you don't have to answer these right now. You can certainly take some time to think, because you'll have some written questions to address next week, and then certainly once you submit your the hard copy report, we'll have some comments on that as well. So yeah, but again, if Justin or Jessica or Tracy, if you have any questions that we want to bring up right now, we'll certainly do that, since we're all on live.
Oh, hi, this is Jessica. I don't think I have a whole lot to add to the questions that were already asked. I think I just also wanted to emphasize a little bit about the costs, I guess, that Tim had mentioned earlier, just that like it would be good to know a little more about, construction costs and maintenance costs of the equipment, because I guess I think it was pretty detailed in terms of how much it would cost to operate, but equipment breaks down. So it would be good to know sort of more, if I'm a client, I want to know, okay, well, how much is it going to cost when this thing breaks?
Yeah.
Okay, I just want to say something. You can hear me, right?
Yes.
Yes.
Okay. So I just wanted to say that we just started this past semester, the spring semester, the chapter for WEF, and that's when we started even thinking about joining the competition, and the whole thing happened, the pandemic. So we ended up moving virtually, and everything was too complicated. So we really tried to do the whole thing and try to finish it in 2 weeks frame, and that's what really got us doing, like, not going into depth, not getting lots of details, trying to do the best we can. Now we weren't supposed to be presenting today. We thought that we're not going to be able to make it. So I just wanted to keep that note that we just started. Like we really, this is our first competition for WEF, and even though we just started the chapter this semester. So I just wanted to say that and leave it there.
Yeah, and based on that, and I let the reviewers know that as well, and you did an amazing job of putting together those elements and presenting today. Especially, I thought a high point was presenting all the different alternatives, because I think you touched on just about all the main ones. So that was an excellent job. So yeah, and I appreciate the again, the time and the effort, and again, you guys did an excellent job. And
thank you.
And with that, I know Tracy didn't have any
questions.
I don't know.
Yeah, I was just going to say too. Yeah, you did a nice job. I know, compressed time. Kind of everybody's locked down. It's hard not to sit around the table. You don't have the opportunity to sit around the table and collaborate. I get it, because that's about a lot what we do when we're designing plants or whatever, is sharing ideas, bouncing things off. So all things considered, did a nice job, and it was nice. I think everybody, their role in presenting did well, going over content and things. So yeah, great. I appreciate the opportunity to listen in.
Hi, this is Justin. Real quick before we close, I also want to add, I like the topic as well. I thought you guys kind of looked for something a little out of the box, different topic, and I thought that was great, and great job today, guys.
Thank you.
Thanks.
Yeah, indeed. And I know Tracy didn't have any questions. I saw a text from her, so she thought you did a great job. Yeah, so with that, we'll kind of wrap up this segment and look forward to the next components, which, as I touched on before, we'll look for your hard copy report, which will also get a separate scoring rating. If you can get that to us by the end of the day, next Tuesday, the 26th. And the step after that will be, we'll provide any additional questions in writing by email by the end of the day on the 27th, and then expect any responses by the end of the day, the next Friday, the 29th. And again, the following week, we'll work out the scoring of both the presentation as well as the hard copy, and we'll share those with you.
And you are going to send some of the question asked today also for them to respond, as Justin mentioned, Chris?
We can do that. Yeah, we'll put those in hard copy format as well.
Sure.
So that, if you have additional thoughts. But again, I want to just say thank you very much. I mean, it's a really great effort for UDC's first design competition entry, even in this challenging time. And I think it sets a great precedent for you guys, continuing on into the future. We look forward to 2021 and onwards, and hopefully that your team will want to continue to participate, because again, I think you did an amazing job for, like you said, being able to put it together in 2 weeks. Just amazing. So
it was only possible because of CWEA leaders, including you, Chris, and I think CWEA was very flexible and very supportive of our chapter and our efforts. So we like to thank you guys on our behalf.
Yep, thank you for the kind words, and again, thanks everybody for your efforts, and we'll be talking soon. Any last comments before we sign off? If not, have a great holiday weekend, everybody, and we'll talk soon.
Thank you very much. Thank you.
Bye.
Thanks.
Bye.
Thanks.